Alright, so in this video I'm going to take a look at an application of SHM. So we're going to look at the application of looking at the bonds in molecules. Bonds aren't a fixed length in molecules. What actually happens is sometimes the bond is shorter, sometimes the bond is longer, and when you see a bond length quoted, what it's giving you is the equilibrium of bond distance. So infrared spectroscopy is a way of measuring what the frequency or the wavelength of the bond's vibration is. So a particular atom with a carbon-hydrogen bond absorbs this particular wavelength of infrared. Now what we want to know is essentially what frequency is that. So we know that for an electromagnetic wave, we have this equation here, and we want frequency, so we essentially need speed divided by wavelength. So it's going to be 3 times 10 to the 8 because it's electromagnetic over 3.40 times 10 to the minus 6. Let's whack that in the old calculator. 3 times 10 to the 8 divided by 3.4 times 10 to the minus 6. What we get is 8.82 times 10 to the 13 hertz. So that's the frequency of the infrared, which will correspond exactly to the frequency of the bond. Right, so we're now going to essentially model it with our mass spring system. So if we imagine we've got our carbon atom, and it's like the hydrogen is being hung from the carbon atom, so the carbon's fixed in space because its mass is much bigger, and the hydrogen is hung from a spring. And so the frequency of an SHM system is given like this for a spring system. So that means to get K, we're going to need to take 2 pi to the other side. Not square root, what am I doing? We're going to square and then multiply by the mass. So we've got the frequency in my calculator already, so times by 2 times by pi squared times by 1.67 times 10 to the minus 27. That's the mass of our hydrogen atom, and that gives us a spring constant of 513 newtons per meter, because that's the unit of a spring constant there. So surprisingly big, actually. All right, so let's crack on. So we've got, if the length at the equilibrium position is this amount, and we've got a maximum length of this, calculate the maximum velocity. So the key here is to work out what the amplitude of your oscillation is, which will be the difference between these two values. So it's going to be 1.21 minus 1.09, and then we're going to have the power of minus 10 to the minus 10. So let's do that first of all. 1.21 minus 1.09 is times 10 to the minus 10 gives us 1.2 times 10 to the minus 11 meters. Now, maximum velocity is 2 pi fa. So we've already got the frequency, so let's multiply our amplitude by 2 pi first of all, and then multiply by our frequency from earlier, so 8.82 times 10 to the power of 13. And that's giving us 6.65 times 10 to the 3 meters per second. So it actually ends up moving pretty quickly, and that would be at the equilibrium position where it has maximum velocity. All right, so that's the lower level questions. Let's move up to something a bit more challenging. All right, so now we're going to look at how we could apply SHM to a car suspension. So a car suspension is made up of 4 springs, so one on each wheel, all acting in parallel. We've got a mass, and we want to know what the natural time period would be. So first of all, let's calculate the equivalent spring constant of 4 springs in parallel. So it's going to be 4 times 50,000 because it's 50 kilonewtons. So that's going to be 2 times 10 to the 5 newtons per meter. Time period is calculated using this equation, like this. So let's put in our value. So our mass is 600 divided by 200,000 square rooted times 2 times pi gives us a time period of 0.34 seconds to 2 significant figures. All right, let's go on to the next part. So it's going over a bump of height 12 centimeters. So the key with that is if it goes over a bump of height 12 centimeters, it's been displaced from the equilibrium position by 12 centimeters, which will be your maximum displacement or your amplitude. So that's the amplitude, and get maximum acceleration, you need 2 pi f all squared a, which is equal to 2 pi over t all squared a. We've got t already, so let's do 2 times pi divided by the answer squared times 0.12 gives us precisely 40 meters per second squared as the acceleration or the maximum acceleration of the object, which would occur actually at the amplitude or initially, essentially. Okay, so then what we're going to do is, as the car's coming down the other side, it begins to uncompress, calculate the velocity of the system when it's extended from its most compressed state by 8 centimeters. So it essentially, its displacement at this particular point in time would be 4 centimeters because it started at 0.12, it's changed by 8, so its displacement is now 0.14 meters. So velocity can be calculated using 2 pi f square root of a squared minus x squared. So it's going to be 2 pi over t square root of 0.12, which is your amplitude, minus 0.04, which is its current displacement. So let's put that in. So 2 times pi divided by 0.34, etc., times the square root of 0.12 squared minus 0.04 squared, close brackets, gives us an overall velocity of 2.09, blah, 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 blah. That's going to be 2.1 meters per second to 2 significant figures. That's the velocity when it's at a displacement of 0.04. Okay, so let's move up to some even more challenging questions than this. Okay, so we've got a general expression of displacement of x equals a cos 2 pi f t. And we've been given a velocity function during an earthquake. So the first thing we're going to do here is essentially work out what the typical velocity is. So velocity is obviously the rate of change of displacement. So that's going to be 2 pi f a, the minus sign, sine 2 pi f t. Okay, so from that we know that 2 pi f is equal to 5.2, which means that f is equal to 5.2 divided by 2 divided by pi, 0.82, that's an 8 by the way, which means the time period is going to be 1 over that, which is 1.2 seconds. We know that 2 pi fa is equal to 4.5, so we're going to do 4.5 divided by 2 divided by pi divided by the frequency, so actually we just do 4.5 divided by 5.2 would give us a over 2 pi f. and that's going to be your amplitude. So your amplitude is just going to be 4.5 over 5.2, because that's 2 pi f, which is 0.87 meters. There. That's the amplitude of oscillation caused by the earthquake. Then it's going to ask you to calculate the acceleration after 2 seconds have passed. So acceleration is again the rate of change of velocity. So that's going to be minus 2 pi f squared a cosine 2 pi f t. So we're going to put t equals to 2 times pi times 1.2 times 2. We need to remember to put our calculator into radians, which I forgot, so let's change that quickly first. So 2 times pi times 1.2 blah 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 times 2. Cosine of that to a minus number, so times 0.87 times by 2 pi f squared, so times by 5.2 squared times minus 1 gives you an answer of minus 13 meters per second to the minus 2 when you whack all those numbers in there. That's your acceleration at that time. Calculate the maximum force experienced by the building. So the first we would need to work out what the maximum acceleration was. So that's going to be 2 pi f squared a. So 2 pi f is 5.2, so that's 5.2 squared times 0.87 is like 23.4 blah blah blah. F equals ma, so it's going to be that we need to multiply by that by 2,000 times another 1,000 to convert tons to kilograms, which gives you 4.7 times 10 to the 7 newtons. So this earthquake has applied a considerable force to the building, and we're going to experience a max when cosine of 2 pi ft is equal to 1, because that's when you get maximum acceleration, which means that essentially 2 pi ft is going to equal 0, or I suppose pi, 2 pi, etc., which means that it's going to be experienced at time equals 0, pi divided by 5.2, 0.60 seconds, let's times that by 2, 1.2 seconds, blah blah blah. So there's actually an infinite number of solutions, because it's essentially every half cycle there. So that would be the times at which this maximum force would be occurring. So that concludes this look at how we can apply SHM in a few different scenarios.